Thank you so much, and thank you for joining. I'm Renu Tewari from LinkedIn, and it's my pleasure to be part of the Flink Forward conference and sharing LinkedIn stream processing journey with all of you. So, before we start, a quick introduction to what LinkedIn is. So, we can describe LinkedIn and what it provides in two words: the economic graph. And what it means is it's the digital representation of the global economy. And what does it consist of? It's like the members, companies, jobs, skills, educational institutions, knowledge. If you can put them all together, you can realize LinkedIn's vision of creating economic opportunity for every member of the global workforce. Now, to do this pretty lofty goal, how does members and these institutions interact with LinkedIn? So what I'm showing you here is a small example applications with which LinkedIn members experience LinkedIn. And a lot of these, if you are a member already, I hope to make some more, converts this talk. What you see is you have your profile page. You can actually look at who looked at your profile. You can look at your connections and maybe recommendations called people you may know. And the jobs that are posted through LinkedIn, you can look at the jobs you may be interested in. You can post and have a feed, and you can look at whoever commented on your post, what's the activity around it, and overall news. And all this, this is a sample of some of the things that we engage directly with members. And all these applications inside run over a lot of technologies that constitute our data infrastructure. And stream processing is one part of that data infrastructure. And in this talk, I'm going to actually focus mostly on our stream processing journey, which supports these applications. Now, any journey, it's good to start looking at how we grew. So what we're going to talk about here is in the last 5 years, our stream processing journey, you can see, has almost exponentially grown in terms of the messages and the messages that are incoming into LinkedIn. We have almost touched 12 trillion now. And the messages that are processed by the stream processing platform, that has also seen an exponential growth. Now, before we continue, I wanted to talk about the use cases that are applied at LinkedIn for stream processing, and they run a gamut of different applications, from data theft detection to notifying our members, classifying the news on what you should see, the relevance of the ads, which ads should be shown to you, understanding the service call graph. How do we standardize the profiles because people input anything in there? How do we do error tracing? How do we sessionize the engagement of the member? This is a small sample of these use cases, and I'm going to use 3 of these use cases to actually show how we have changed the architecture and how it has evolved over time. So the first use case, this is the original problem that LinkedIn started with. And if you think about it, you can update your profile. The profile, you can put in what your title is. A lot of people get very creative about their title. And they could put things like ninja coder, bug repeller, a rock star programmer. And now for LinkedIn to use your title and what your job description is and explain and attach jobs that you may be interested in, requires us to actually standardize that title. So we have to run some machine learning logic to actually say all these interesting titles actually map to software developer. so that the internal applications that rely on this profile information can share with you more relevant data. Now, how does this job title standardizer work? It uses a lot of technologies, but we're going to focus on the stream processing side of how this works. So this was the original architecture. If you look at the top part, you have your source of truth data, which includes the jobs and the profiles of all the members. It is stored in a document store. And there is a change capture stream that is tracking all the changes that are happening to the source of truth data. And that is going into our message queue. And there is a job standardizer job that runs on the stream processing engine that is going to react to the changes that are happening on the source of truth data. And it's going to do the processing, leveraging a machine learning model, and then the derived data flows out. Now, what happens when people change their profile or the model changes based on some more understanding on how should we do this mapping? Or I need to change now the set of jobs that I need to show to you because your profile mapping has changed. So there is another job that runs, which is the reprocessing job, which we call the grandfathering processor. And it needs to look at a snapshot of this source of truth data. And the way it gets access to this snapshot is we are periodically pushing the snapshots into Hadoop, into HDFS. And now I have a change stream from that, reading out that data into this reprocessing job. And so I'm getting historical data from a previous snapshot that I'm going to rewind and reprocess every time there is some change in the model. And this is going to run not all the time, this will run periodically. And if you look at the number of hops now the data has made back into the stream processing engine, it has actually gone through multiple layers of data copies and multiple interactions with various other systems before it is made available. So now this whole process makes it pretty slow. And I can actually summarize this whole flow into what stream processing folks are very familiar with is the Kappa architecture, right? So if you look at our nearline processing standardization view, it follows what the Kappa architecture view is, which is everything is done in the stream processing engine. It is not the traditional Lambda architecture where you kind of split between nearline and offline. So if you view it in that architecture, if you think of this big message queue that is being used by the stream processing engine, the real-time data that is being continuously updated is being read by this real-time processor, and the grandfathering processor is reprocessing the data where you're taking this periodic snapshot and updating and backfilling the earlier data so that this can start from the oldest offset. And this is the traditional Kappa architecture that we're doing, but you have to realize that this snapshot data actually took a long journey before it arrived here because snapshots in just, keeping that much state are stored not in nearline, but in offline, and then they are brought in to the nearline stream. And this, real-time processor is running 24/7. The grandfathering processor is running periodically. And this is going to trigger a whole latency in how quickly I can respond to these changes, because now data has actually flown through multiple data copies. So what do we want to do here? So this is what we had earlier. More recently, we are actually doing what we call a Lambda redux. We're going to re-look at the Lambda architecture again and see why did it not work earlier. One of the big reasons that it doesn't work is having applications write their jobs on two platforms using different APIs. It makes it really hard to maintain these jobs. Every time I change, I need to change two platforms. It becomes an operational nightmare. So when we did this Lambda redux, if you look at the top part, it's the same flow. You have your real-time processor, the job standardizer running there. But what we changed is the reprocessing that was done by moving the data back into the stream processing stream by actually moving the processing back to offline. So you have your historical data of jobs and profiles, and the offline processing can be done using the offline processing engine, maybe Spark, maybe Hadoop. And the difference is that now we use the same API. So the API that was used for running that job can be the same API we use for running it here, so that I really don't need to change my application significantly to make it run on two platforms. And those changes have happened because there's a bigger adoption of SQL, and there's a bigger adoption of Apache Beam that lets us leverage this duality across different engines. And now I have a much cleaner flow because I don't have to copy data that often, and I can actually reduce cost in leveraging this. So this has been one change in how we did stream processing earlier for our canonical use case of title standardization to now what we do again. Now, if you look at Lambda, I think we talked about the APIs becoming common, but other problems still remain. So there are still challenges. How do you orchestrate a job across these two platforms? How do I make the same data store available in the nearline platform, because it may have the right connectors for a specific data stores, whereas the offline platform may not have that. So you have to make sure that you have the same access available to you. And then when you move jobs to run from nearline to offline, you have to understand that what is the concept of time between the two, because we said we're going to take a snapshot, which could have been a daily snapshot. And where does that time end, and where does the real-time stream start, right? These have been challenges for a long time, and some of these problems are what we are exploring in the future. The other thing is cross-platform metadata. Those challenges still remain because I don't know the physical versus the logical instantiation of that data set, because one platform may be talking about topics, the other may be talking about files. I really need to map that they're talking about the same data set. So this was one use case. Let's look at another use case. This is also a very important use case for LinkedIn, where we need to decide on how do we notify our members on all the activity that has happened. For example, you may get a notification that somebody in your connections list has a work anniversary, maybe it's their birthday, maybe somebody clicked on your post and liked it. Somebody's messaged you for a particular one-on-one message. Or they could be like a certain activity that you have had on some other site that is connected. And all these notifications need to be shown to the member at the appropriate time. So you need to decide on when do I show this, how do I show that, how frequently I show it. Because if you overflood the notifications, it's going to ruin the member experience. So this application called ATC has to figure out what is the right cadence that we follow and what is the right channel that we should pick to notify the member. Now, this is how the nearline processing for notifications was deployed. And it actually went through a few iterations, and we'll talk about what we are doing now. So you have the source of truth data, and you have a lot of signals on member activity that is flowing into this stream processing engine. Now, the jobs that are running, to simplify it, we have the relevance job that's going to figure out the relevance of the signal and should it convert to a notification. And that is going to create a lot of state while it's doing this nearline processing. And this state is stored locally because you want to have very high throughput, low latency access to that state. So it's stored in RocksDB, local to that machine. Now, what happens if the machine fails? So there is this state is also there in a changelog topic in Kafka so that when something fails, we could recover from it. So if there is a failure, you can restart the job on another node, and you can get the state from that changelog topic, restore it, and start your processing again. Now, what the problem that happens, especially in these kind of jobs, the state is pretty large. And when the state is large, as you can imagine, the restore time is really high too. So that defeats the SLAs that this application needs to promise to its customers on how quickly and how responsive notifications are. So what should we do for fixing that? So the earlier approach that we had taken was to create a hot standby container. So just as we had done the restore on a failure, how about we do the restore all the time? So we keep this state available on another node in a hot standby mode so that any changes that are happening are also propagated to this hot standby. And if there is a failure, I could just move to that. What's the problem in this approach? The big problem is that, of course, you have increased your cost because you're going to have two copies. You have also made the load balancing a little trickier because every time something fails, I need to understand that that job needs to start on a particular node because it needs to have affinity to that hot standby state. And that now makes it really hard when you're going to have imbalances in your system. I do not have the flexibility of starting that job anywhere. I need to start it only on the limited set of where the hot standby exists. So in order to actually fix this, we came up with a different approach on how we do the restore on a failure. So this is the process now. What happens is instead of storing the RocksDB local state in the changelog topic, I'm going to leverage a similar idea as RocksDB Cloud, which lets you actually store the internal files of RocksDB in an external blob store. Or if you're doing a public cloud deployment, this could be whatever public cloud storage offering that cloud provider provides, or it could be an object store if you're running internally that has the similar behavior. It first lowers cost, plus it is available from all the nodes because this is now shared storage, and it has a good throughput and latency numbers that kind of meet our requirements. So the similar idea that RocksDB Cloud has is moving these files, internal files of RocksDB to the cloud, and then that enables you to restore on any node that has access, which all the nodes in this cluster have access to this blob store. So you can pick any node where I can restore this container. You can get online very quickly because all the data doesn't have to be copied before RocksDB is ready. And you can pull in things in the background. So now we kill two birds with one stone. We have a recovery path, which maintains the throughput and latency that we need for these high state jobs, as well as I don't have to pay an arm and a leg for the cost of this system. So this is the direction that we have gone for very large state jobs. But there are still challenges on extremely large local state. As we said, we only talked about the restart time. So there is the work that we've done actually fixes the restart time, but there are some other problems that you will always have very hot containers. You have to balance the load. You have to figure out what is the right provisioning you do for these resources, because if they're going to get overloaded, you need to be proactive on how you move things around to maintain balance in the cluster. Otherwise, you're going to start seeing delays in certain jobs. So those were like two use cases. Let's look at another one. Given that there is a big uptick in machine learning and machine learning applications across the board, especially in data analysis and what we make out of it. So our third use case is add relevance. So what does that mean? So you have members, they have their connections, they have activity on the LinkedIn side, they have activity on an advertiser side, they have their profile data. And we have an advertiser who wants a particular ad based on some targeting criteria to be shown to that member. So we run these analytics that is going to look at all these signals and try to match it based on the ad targeting criteria. And then you have the ad serving platform that serves the ad. This is something that all internet services use, because that's how they work, by generating ad revenue. And this is kind of the crux of how the ad relevance system works. Now, what do we do with these machine learning models that we create to do this mapping? Now, a lot of these models typically run offline, because you train the data set and then you build your model and then you use that to create this targeting data. Now, the offline training and service is typically has poor data freshness by just by design, because you're going to have offline data that is going to be curated for monthly, weekly, daily data sets. So you're going to never be reacting instantly to an activity. And then there is a long delay in production. So you kind of want the best of both worlds. That can I do my model training in offline, as well as can I adjust to what changes are happening instantaneously. So the nearline processing for ads AI, how does it look like? So you have a feature marketplace. A feature is basically anything. If the number of clicks you've made or the time you've lingered between when you looked at a particular page, all that constitutes a feature. Anything could be a feature. That's the up to the AI engineers on how you define it. And then you have an offline global model that is going to train on all this data. And then you have a real-time stream coming in, which is your activity. That's your page view event and what you have done on your LinkedIn profile, or how you have engaged with the LinkedIn app. And then the offline model is, of course, doing the scoring of trying to fit this feature data into the scored data that is coming out, and it's coming in as a stream. And then the other side is your ads impressions. So what are the ads that you have been looking at? So the stream processing part of this pipeline has a repartitioner job, which the whole purpose of that is to make sure that all the data belonging to a particular member and the access, the clicks and the impressions all land up on the same engine and the same partition. Because you could have, we run multiple data centers, you could have a traffic shift where your click and your impression may happen on two different data centers. So you want to make sure everything happens together. So that's what the repartitioning is all about. And then you have your feature data generator job that is going to generate the feature data based on now the real time activity of the member. And that will generate a training data event. So now you have your offline model trained on offline data, and now you have a training data event happening in nearline. And we are going to actually embellish this learner, the Lambda learner, which is going to use the nearline activity to improve the model. So I'm going to use the Lambda learner to actually change my nearline model, the machine learning model that was offline, by this nearline data. And after that, now I have my recommendation that happens to be visible to the member. Now, if you look at this whole flow, you will see that you are having a much more agile platform, because not only is your offline data being used to build very robust models, you're able to adjust that model to your most recent activity, because most people are looking at responses on what they're doing right now. So you kind of see the right ad based on what your recent activity is. And this is a very powerful model. It can be used for a lot of the other AI based applications to have this feature of reinforced learning with real time data. Now, there are still a lot of challenges with nearline AI model training. First of all, is the window size selection. You have to decide between availability and accuracy to grow what's the right size of window I need to use to create this training data event. And the other thing, as I talked about, is given we have traffic shifts because of failures, you may have your activity on one data center, whereas the impression happened on another. And when we need to do these joins, we need to be very aware of that there are different colos that could be tracking different activity. The other problem is repartitioning the data. It's very dependent on the schema of the upstream data. So you have to make sure that you handle schema evolutions correctly. And another challenge that actually remains, as we talked about earlier, is handling, if you have bad data and you're going to want to rewind and backfill it, you need to know the ability on what is the exact start and end times. And this has been a challenge across the board. When we move data across different systems, how do you know what the times it actually represents? So these were like three use cases. We talked about what we did earlier, and as we realized that the scale has changed, the states have increased, the machine learning reactivity has to change. We want to make sure that we remain adaptive to these changes as we continue our journey. So what's next? What are the challenges that remain in stream processing? So one of the big challenges that we have is when the scale has increased a lot, we need to auto size the jobs correctly. We need to make that independent of our users, that we can figure out as you deploy what the size of the job should be based on history. The other that is very important is elasticity and auto scaling. And what does that mean? And what I mean there is, more and more of these deployments are going to happen on public cloud systems. And you really need to leverage the elasticity of the cloud on how you're going to grow your stream processing job, how it's going to scale and leverage that available resources to you. So you need to be, don't need to over provision. you need to actually auto scale. So you have to have elasticity in the system. And this is really difficult with stateful jobs because you have state, as we saw, we try to keep it local. How do I actually scale my system while dealing with that local state? And the other problem is trying to make these jobs more templatized so that it's much easier for application writers to leverage this. They don't need to understand new concepts, new APIs. There's a lot of repetition that's happening in these jobs. A lot of them start with repartitioning, basic filtering. So all these things can be templatized on. That makes it very easy for application builders to build stream processing jobs because that has been a big hump and a big learning curve for application writers. So as far as possible, if we can make it easy to use and easy to build, there will be a lot more adoption. And the third or the fourth issue that we've been talking about, actually mentioned it across a bunch of these use cases, was handling time. So as we saw that whenever you want to reprocess or every time you move between systems or data stores, you lose track of which point in time you are. And how do I make sure that I am continuously, seamlessly moving across time? And these time boundaries are very ad hoc these days. We kind of do guessworks. You kind of over rewind because you don't have exact idea of what the point in time is. There is no way to track it. There is no way to access it. And there's no way to guarantee that the same time prevails across these systems. So handling that, handling a better way to use that to make things much more seamless and continuous is very important next step. The other is metadata across engines. As we saw that different systems have a different physical representation of the data. Having the ability to access it as a logical construct and then map it to the physical construct is something that needs to be solved across these engines. And the fifth one is materialized views. So if you see that a lot of these stream processing jobs may be running very similar steps in their pipeline. And a lot of this could be materialized and available so that you don't have to repeat the same step, especially on machine learning models. These things are repeated again and again. And if I could materialize this view, have the ability to access it, we could simplify a lot of the overheads that we see in these jobs. And last but not the least, we talked about Kappa, Lambda, how we started with a Kappa architecture, which enabled us to do all the processing on the stream processing engine. And then we actually did a reverse back to Lambda, because it simplified the amount of data movement and the delays that happened. But ideally, you want a converged, either a converged platform or a converged methodology so that I could run my jobs on any platform that is the most optimal for that and has the access to the data for that. So once we have that, you can actually build these applications that don't have to worry about the quirks of the engine, of the quirks of the connectors that are available at that platform. So with that, I want to take you to the end. So thank you for joining. And we are exploring Flink as one of the platforms we want to introduce into our family of stream processing platforms. And hopefully, when we do the next Flink Forward, we would talk about Flink in LinkedIn. So thank you all.